All right, can everyone hear me and see my slides?
Yes, we can.
Great. All right, I am Brian Pierre with the Electric Power Systems Research Department at Sandia National Laboratories, and we've been working on some research and development for electric grid resilience and reliability co-optimization. So creating optimization models to identify the optimal investments to improve resilience, reliability, and a combination of the two, and see the trade-offs between investing an entire budget, for example, in resilience versus your entire budget in reliability, or if there's some optimal spot on a Pareto frontier to invest in both and get a large improvement in both your reliability and your resilience metrics. Briefly mention some partnerships. The funding for this was a laboratory-directed research and development program at Sandia that led to Department of Energy funding in the Advanced Grid Modeling program. I'll give a brief introduction about reliability and resilience, then I'll jump into the optimization models for our grid reliability optimization models, grid resilience optimization, where we look at this from three different perspectives. So we look at it from optimal investments or planning perspective, where we're looking many years in advance. What are the optimal investment package options to improve our resilience metrics? Next is from a preemptive action process. So if you're given a warning or a forecast that an event may occur, how can you help brace your system for that event if it does occur? And lastly, a restoration process. So the optimal multi-time period restoration process to restore service to critical loads once one of these catastrophic events has been realized. Also mentioned, we try to include grid dynamics and cascading failures within our decision-making process, because often some of the worst case outages in history have to do with cascading failures. Then I'll go into the co-optimization of reliability and resilience and showing trade-offs between investing in one or the other more heavily. And then finally, if we have time, I'll briefly discuss some newer work where we're trying to identify critical nodes and vulnerable nodes within the grid. So the overall goals here is to develop these optimization models to improve resilience, reliability, or a weighted combination of the two. We want to help utilities see the trade-offs between investing more heavily in one or the other, help utilities develop rate recovery cases to help justify these large-scale investments by quantifying how these investment packages that they're selecting will improve both their reliability and resilience. We also want to inform utilities, stakeholders, DOE, of cost-effective infrastructure investment decisions to improve reliability and resilience. The brief introduction on reliability and resilience. On the reliability side, we're looking at high-frequency, low-consequence events. So these are things that are cause local outages that occur every day, such as small-scale outages from animals or wind, trees. On the resilience side, we're looking at it from a high-consequence, less frequent events. So these are large-scale events that occur less often, such as severe wildfires, earthquakes, severe winter storms. As far as metrics on the reliability side, it's pretty well defined. We look at minimizing SAIDI and safety metrics. And on the resilience side, in this project, we mainly look at minimizing weighted load shed over a multi-time period restoration process. So there are others, colleagues at Sandia, that look at a lot of different metrics for resilience as well, such as societal impact and economic consequences. But for our purposes, we're mainly looking on power systems related side and looking at weighted load shed. Current practice on the reliability side is often to take a more reactive method instead of a proactive method. For example, a utility may look at their past year of outages, go down that list and start fixing the worst events that happened in the past year. And this is definitely a way to improve resilience or improve your SAIDI and safety metrics. But our R&D focuses more on a proactive method rather than reactive, and a probabilistic approach. And in the end, we developed this optimization methodology to identify the optimal small-scale investments to improve reliability. On the resilience side, there's still not a full fully accepted methodology for resilience, and a lot of this work is still in the research stage or specific application stage, such as focusing on specific technologies such as microgrids or energy storage. This R&D, it focuses on this three-stage methodology to capture multiple timeframes. So this investment planning, preemptive action decisions, and restoration process. So we've developed multiple optimization models to capture the optimal decisions within each of these stages. And then finally, we do a co-optimization to view the trade-offs between investing in reliability and resilience. One thing I just thought I'd point out is that it's often that utilities are incentivized to be reliable, but there are less incentives right now. I know California's been working on this, but less incentives to become resilient. So some utilities will have performance-based regulation or at least internal goals to meet certain reliability metrics, such as meeting safety and safety metric goals. And I'll also say that some large-scale events are removed from the calculation of safety and safety, which actually causes even less incentive to become resilient. So in general, this is a topic for another discussion, just improving incentives to become resilient. On the reliability optimization framework that we've developed, the primary input to this model is historical outage data. So we worked with a utility in the northeastern US that supplied us with 5 years of historical outage data. What we do with that data is we characterize it into probability density functions. Then we use that probability data set to create future year scenarios of outage data sets. So if we were looking at 2022, we would create thousands of data sets that are based on the historical data of what could happen in 2022. And so we would use those thousands of data sets that are created from the historical data through sampling our probability density functions. Those thousands of data sets are then the input into our optimization model. The optimization model would also need investment impact and cost data. I'll mention just in general, cost data is very limited at the national labs, or at least at Sandia National Labs. So that would be an input a utility would provide, or the user of this model. And then our optimization model selects the optimal investments to improve and minimize the safety and safety metrics of the grid in question that we're looking at. And it would be minimizing the safety and safety of the thousands of future year scenarios. It would also list the expected new safety and safety if you were to apply the upgrade options that the optimization model selected. So we applied this on that northeastern utility in the US. And as you increase your budget, again, I'll mention budget-wise, take it in more of a relative term rather than a firm term. We would improve our safety and safety metrics significantly by identifying the optimal small-scale investments to improve system reliability. We also wanted to see if you weighted safety or safety more heavily, how that would change the result. So it does change your investment decisions, whether or not you want to improve your safety more or your safety more. But the overall metrics were pretty similar. This is because safety and safety both rely on the number of customers affected. As far as scalability of this optimization model, it has great scalability for large data sets and larger systems. And we have a couple publications on this work. Now to get into the resilience aspect that I think this group is a little more interested in. We look at this from 3 different aspects. So a long-term planning. So these are the optimal investments or hardening decisions when we consider years in advance trying to become resilient, typically to one specific threat scenario, but it is possible to try and become resilient to multiple threat scenarios. I should say multiple threats. So it's always, the model always works with many threat scenarios, but we have typically looked at only one threat, such as hurricanes, earthquakes, winter storms. However, it is possible to use this where you're trying to become resilient to multiple threats. And then The second aspect of this work is the preemptive action. So you're given a warning or a forecast that an event may take place. So for example, you're given a forecast that winter storms may occur. How can you help redispatch, reconfigure, and pre-position resources to help brace for that event if and when it does occur? And third, the optimal restoration process. So the event has happened. What's the optimal multi-time period restoration to optimally return critical loads to service? So we connect stages 1 and 3 together in a 2-stage stochastic optimization model. We also do that with stages 2 and 3, connecting preemptive action and restoration. This is one of the only somewhat math slides, but primarily it's just saying that in the first stage, in the investment and planning stage, we try and minimize the tail or the worst case scenario in events that could occur. We want to stop the category 5 storms from causing the great catastrophic damage. So we're focused on reducing the consequence of the worst case scenarios in the first stage. In the second stage, we're now given a forecast that an event may occur, and our accuracy of these scenarios is much higher because we have this forecast. So say a 24-hour warning and forecast that an event may occur. So now we try and minimize the expected value or your average consequence of all the scenarios that you're trying to become resilient to. And in the third stage, the restoration, a single one of those scenarios has occurred or the event has happened. We're trying to minimize the weighted load shed throughout a multi-time period restoration process. So I'll give 2 examples of some of this work on the preemptive action and restoration. So in the first example, we're given a 24-hour warning that a hurricane will strike a city. We want to know how to optimally dispatch limited flood walls around substations to minimize load shed. And so I will mention that although some of these examples are looking at hurricanes or winter storms, a lot of these models were developed to be threat agnostic so that we can simply change the front end of our modeling framework to be looking at scenarios of wildfires, earthquakes, rather than hurricanes, winter storms, and so forth. So but I just mentioned that as I show these 2 examples. And the second example is given a 24-hour warning a winter storm will occur. How can you redispatch your generation to minimize load shed? So this is looking at it instead of doing a full economic dispatch for your generation, instead looking at the objective function instead of fully minimizing costs during this short-term window of the winter storm. Rather, you're trying to minimize weighted load shed in the system. So it slightly changes things. So in the winter storm example on the right, this is a top plot is the baseline. So optimizing over 100 winter storm possibilities. So we took that forecast of a winter storm. We create 100 different winter storm scenarios. So how that winter storm could impact the grid. And then we run our optimization model to identify the redispatch of our generators before the winter storm hits that would minimize the consequence of the event if and when it does occur. So the top is baseline with no redispatch. So you're simply continuing normal operation. And on the bottom is now you've changed your objective to minimizing load shed over these 100 winter storm scenarios. You redispatch your generators in advance of the winter storm, and you can significantly reduce your expected load shed when and if that winter storm does occur. On the left, we're doing something very similar, but for hurricane scenarios. So in this case, it was pre-positioning some resources in advance of the event. And so simply by pre-positioning resources in the optimal locations, we're able to significantly reduce the consequence of the expected consequence of those hurricane scenarios. Mentioning that hurricane scenarios, again, this work was done on the Texas area. So in the Houston area, we were looking at creating 25 hurricane scenarios based on Hurricane Harvey, which hit the Houston area back in 2017. And we're trying to minimize the consequence of those 25 hurricane scenarios by pre-positioning these flood barriers. As we increase our access to flood barriers, we can decrease the expected load shed. We ran this on the Texas 2000 system, so that's the power system that was used. It's a mock-up of the ERCOT grid. And on the right, these figures are showing the placement locations for the flood barriers if you were given a warning, a 24-hour, 48-hour warning that a hurricane may hit this area of the system. Now I'll get into the investment aspect along with restoration. So this is now looking, instead of the preemptive action decisions, looking at it more of a long-term planning process. And then if one of those events is realized, these catastrophic events, the multi-time period optimal restoration process is considered in the third stage. So for one of our examples, we created 45 hurricane scenarios, and we applied those to our optimization model to minimize the weighted load shed over those 45 scenarios, simply by investing in the optimal 5 components in the system to reduce load shed. So on the top plot is the load shed, weighted load shed in the system for all 45 scenarios, given no investments were made. So you can see the green line is showing the expected load shed, and the red line is showing your worst case scenarios. In the middle plot, we apply our optimization model to select the optimal 5 components to harden. Now those 45 hurricane scenarios are analyzed with the 5 components hardened to 2 hurricanes. And by minimizing the expected value, we can significantly reduce the consequence of those hurricane scenarios. Again, green line being the expected value, red line being the worst case. So next, we wanted to try and see how, if we change the objective function from minimizing the expected value to minimizing the conditional value at risk, so that's the worst case scenarios, how that would change the investments and change the impact of those 45 hurricane scenarios. So as you can see, the red line is significantly further left, meaning that the consequence of these worst case hurricanes were significantly reduced with this new objective function, the conditional value at risk. There is a slight trade-off, though. The expected value has gotten slightly worse because it's no longer the goal of the optimization model. And this sort of work, although we apply it here to hurricanes, we believe it could be also applied to things such as wildfires or earthquakes. So to continue that modeling work, this is looking at the optimal restoration process over the 24 hours after the hurricane occurs. So the top plot is the hurricane has started. You see load shed throughout the system, represented by the black line is total load, and the red line is no investments, the load shed during this hurricane scenario. And then the other colored lines are, as you invest more, you have less load shed as expected during this hurricane scenario. We also looked at modeling this with different power flow approximations. So I'll mention optimization formulations. Scalability can sometimes be a concern. So using a full AC power flow within an optimization model is extremely difficult as far as scalability. So we use 2 different power flow, the classic DC power flow approximation in our model, along with a more advanced approximation, the second order cone programming model. We also have a couple publications on some of this work. That might have got into a little bit of the details there, but next, our aspect of this work was we wanted to somehow address cascading failures within our decision-making process. So often some of the worst case blackouts in history have been due to cascading failures, such as a blackout in the northeastern US in 2003, or the West Coast in 1996. A lot of these had to do with cascading failures that ended up triggering many things to go offline. And so we want to somehow include this information of these transient and dynamics of the power system within our decision-making process so that our optimal decisions protect against these cascading failures as well. So in this example, it was on an IEEE test system. We were running an earthquake scenario where the earthquake tripped offline 2 high voltage transmission lines and 3 generators. The initial event occurs. This caused significant generation and load shed, but the frequency continued to drop. So under frequency load shedding was triggered. This ended up leading to more voltage issues in this specific area of the system. So it ended up the entire area of the grid went offline, which led to even further problems in other nearby areas as well, and led to more areas of the system leading to full collapse. So this is one of the worst case scenarios that can occur, right? Is a full collapse scenario where it's a wide scale blackout. So this is some of the information that we want to capture this information somehow within our decision-making process, rather than only looking at steady state considerations. So when we model these events with transients and dynamics, rather than modeling with just steady state power flows, we see a significant difference in the initial impact measured. So if we were to model with a DC power flow, in the bottom left plot, this blue line is one of the earthquake scenarios, and it measures 500 megawatts of load shed during the initial impact of that earthquake. And then as time goes on, you slowly recover over the first 12 hours after the earthquake. However, when we measure the same earthquake scenario, but we look at it in much more detail with a cascading and dynamics model rather than just a steady state model, we see a much more significant impact of that scenario. So instead of 500 megawatts, now we're at 6,000 megawatts. So it's significantly different because these earthquakes ended up triggering some cascading problems to occur. So this is just pointing out that the decision-making process, when looking at these large-scale events where multiple components are removed from service, they should be somehow including information of power system dynamics and cascades. So we applied this model into our investment optimization work that was just presented right before this. So we're adding in the dynamics and cascading information within the optimization model to identify the optimal hardening locations in the system, the optimal investment packages, to improve our system resilience to these 45 hurricane scenarios. In this case, we were looking at 3 earthquake scenarios. So we're trying to find the optimal investment packages to improve resilience to these 3 earthquake scenarios while considering cascades and transients. So we were able to identify the optimal components to harden and significantly improve the resilience. One downside of then including the transients was it limited our scalability in certain aspects of this model. So the way this model would end up being used is, let's say a utility or an organization has identified 10 possible investment packages to improve resilience. Well, this then can help identify the single best out of those 10 that can improve resilience while considering cascading failures and these large scale events that can occur. Now, those past slides have kind of been leading up to some of this work on co-optimization. So where we were trying to show the trade-offs of investing more heavily in reliability versus resilience. And so the main thing I want to point out here is to this plot on the left. This is showing Pareto frontiers of different investment budgets. If you were to invest that entire budget in resilience, entire budget in reliability, or some combination of the two. So this top point here is an investment of $4 million is the budget that you have to invest in resilience and reliability. And so this point, for example, where my laser pointer is, is looking at you use all 4 million on resilience. So you decide not to worry about reliability, improve your resilience. You get an improvement of about 49% in your resilience metric. So a normalized 1.0 down to 0.5 or so for your resilience. Now we want to show this next point on the Pareto frontier. This says if you were to invest instead of 100% in resilience of your budget, you instead invest 80% in resilience and 20% in reliability. You still get almost the same improvement in resilience. So now instead of going an improvement of 50%, you have an improvement of 48%. But now you also have a 21% improvement in your reliability metrics, so improving your SAIDI and safety in the system. So these are the kind of information that we want to get out there and help utilities understand these trade-offs between investing more heavily in reliability, resilience, and maybe there's some optimal point on these Pareto frontiers that can indicate the perfect investment package for a utility to meet goals of reliability and goals of resilience. So a little summary on the optimization models. On the resilience side, we're minimizing weighted load shed. We use a multi-time period restoration process. We have 2 different power flow models to use within this. We have the option to include optimal transmission switching, but it is computationally expensive. We have that option to include initial transients and cascades. I mentioned that, but it does limit certain aspects of our scalability of the model. And then this work is a stochastic optimization model. So we're looking at multiple scenarios to become resilient too. On the reliability side, we're trying to minimize SAIDI and safety metrics. We have 2 different models for this work, and you can either run this on raw historical data or the more probabilistic proactive approach. It's a either or choice. That wraps up most of the optimization formulation. I'll briefly mention some of our recent work on critical nodes and vulnerable nodes. So our goal here is to identify nodes in the system that are critical to resilience. So this would be components, generators, transformers, transmission lines, substations that would be critical to resilience of the system. So in this plot, we're looking at different threat scenarios. So again, we have thousands of these threat scenarios. So you can think of it as thousands of earthquake scenarios. Well, we look at the locations of those scenarios, different locations of these earthquakes, for example, trigger different component clusters to trip offline. So different component clusters end up leading to different impacts to the system. So this allows us then to backtrack. So if we look at the worst case impacts of the system, we can backtrack and say, okay, cluster C5 and C9, these components within these clusters ended up leading to greater impacts on the system. So this information would indicate that those components within those clusters are more critical to our resilience. So this is just valuable information for system awareness, and then it can also be helpful in the decision-making process to improve resilience. With that, I'll conclude and just highlight that I presented many different optimization models to improve resilience and/or reliability. On the reliability side, we're looking at optimal small-scale investments to improve grid reliability from a proactive approach. On the resilience side, we're looking at 3 different aspects. So from a planning perspective, where we're trying to identify the optimal components to greatly improve our resilience to specified threats. On the preemptive action resilience side, so given a warning that an event may occur, how we can help brace our system for that event, given a 24-hour warning. Next aspect is the optimal multi-time period restoration process. So now one of these catastrophic events has occurred, how to restore service to your critical loads in the system. And then I'll mention that in this decisions for improving resilience, we need to account for transients and cascading failures, because if decisions are based solely on steady states, they might not address solely based on steady states, they might not address the cascading failures, which can often be the worst case contingencies. And then lastly, I briefly mentioned some work on identifying critical nodes to help improve system awareness and improve the decision-making process. Future work, we want to apply these models with partner utilities to identify real decisions. We want to employ these models within existing planning tools, and we want to expand some of this work to include other objectives other than just resilience and reliability, such as decarbonization and energy equity. And then we want to work on some of the scalability of these models, such as trying to apply a full 3-stage optimization model, which is extremely difficult and would need improved scalability. And then also just add some additional features to each stage of the optimization model. And with that, are there any questions? Thank you.
Go. Can you see my presentation? I assume yes.
Yes, we can, Miguel. Thank you.
Okay.
Yes, we can. And I'm resuming recording. Thank you.
All right. So, as I said, my name is Miguel Heleno. I'm a researcher at Lawrence Berkeley National Laboratory, and I am presenting this work called risk-controlled expansion planning with distributed resources. And this tool, Repair, is funded by the Advanced Grid Modeling Program at OE, Office of Electricity, and by the Microgrids R&D program at Office of Electricity. So this is the project team is myself and 2 other people that are working in the development of the model and this tool, and Joe Eto. I guess most of you know Joe from this group too. So I'm here mostly to talk about focusing on the problem of expansion planning and distinguishing reliability and resiliency, specifically the problem of reliability, addressing reliability and resiliency in the investment and planning of distribution grids, which, you know, nowadays there are many options in terms of assets. We can talk about, you know, new substation, new connection, so new route, hardening existing lines, developing DRs like batteries or distributed generation, or even microgrids, improving the topological flexibility of the network with circuit breakers, with reclosers. So there are many options to improve reliability and resilience of distribution grids. But like when we're talking about the portfolio of options, in terms of investments, we also have to bear in mind that, as Brian said and explained, there is, you know, a lot of things that can go wrong, and we typically describe this in a simplified way in some sort of like probability of some energy not supplied. And when we organize these events and these different probabilities of things of outages, let's say, and the energy that is not served in these outages, we can organize this in some sort of, you know, a curve like this. And when you deal with reliability, we try to control the expected value of these type of curves, not only in terms of the energy, but in terms of the frequency of or duration of these events. So, but it's always an expected value. And when we look at resilience, we look at the tail of these events. So at the high impact, low probability event. So basically, the events that can take significant part of the load, and they are very, very rare. So the main question here is, you know, when you in the exercise of like selecting which of these assets to invest in the grid. How can we handle both the expected value and the risk of this, and what combination of assets can actually produce the more risk mitigation or address more the routine aspects or the expected aspects of this. So, and the other question is, what are the trade-offs? So what are the trade-offs between costs, between optimizing for reliability, optimizing for efficiency? So we started with this question like 2 years ago, and we prepared a very simple case with Commonwealth Edison in Chicago, a utility we are collaborating with. So last year we decided to, how to demonstrate this question first with a simple example. So what we did was we took part of one of their feeders, so just a portion of one of their main feeders within Commonwealth Edison reliability program, and we so this is the system plan, the original plan, and we compared with other plans they had, approved plans they had for this feeder. Basically, we looked how this feeder evolved in time. So first of all, they had this feeder was a very simple 4 kV overhead feeder with a connection to the main 12 kV part. And first there was like an investment in a new connection, so a new loop in this feeder created by a new cable, the first cable, because all the rest is overhead. So there was a new cable created, and we call that an intermediate plan. This was a reliability investment that ComEd got approved for. And on top of that, now last year, ComEd decided to invest in hardening the south part of this feeder, basically transforming these lines into cables, exploring these now at 12 kV, so taking advantage of the existing cable they had constructed, and operate now this cable at 4 kV, at 12 kV, and creating a new connection here in the south to a different 12 kV connection. So they kind of like close this loop, fully harden this south part, but of course they let the other part as 4 kV. So and because they have now, the system has 2 different voltages, they had to open this connection here. So what happened was, what happened here was like their resilient plan actually disconnected, improved the hardened the south part of the feeder, but it actually decreased the connectivity of the north part of the feeder. So the north part of the feeder is actually like now fully radial. So basically, this is an example where a resilient investment or a partial resilient investment affected the overall reliability of the system. And then we evaluated their outage profile in this area, so the typical outage that can happen, basically like a historical of 10 years of outage data in this area. We also evaluated, this was created like some critical scenarios based on their data. We created different scenarios of storms that could hit different parts of the feeder and can disconnect multiple overhead lines. These scenarios, we assume that they were very rare, so happen once every 70 years. And we also consider, which is like very common in that area, some flood events. So flooding here in the main central area of the feeder, but with 2 different magnitudes, these 2 type of events, but also these events being very rare, meaning once every 70 years. So we have their routine outages, we have their critical scenarios, I mean their high impact, low probability scenarios, and we basically derive their typically reliability results for each of those, for the evolution of that feeder. So the original system, as you can see, there was an improvement in reliability with their first loop that they added, and on top of that, when they hardened the south part of the feeder, there was and although there was an improvement in the duration of the frequencies, there was actually the frequency, the safety became a little bit worse, and that has to do with that opening, the fact that the north part of the feeder became less connected because now the feeder are operated at 2 different voltages. So this was the case where like actually an investment in the hardening investment slightly decreased the system reliability. And of course, when we look at the resilience results, so the CVAR of not serving the demand. So when you look at the tail of the distribution of the loss of load in this feeder, we can see that, you know, both investments, this intermediate system and then the final system hardening solution pushed this curve towards the left, especially the hardening investment. So we can see significant resilience improvement, both in the CVAR and the worst case scenario. So when we actually look at the probability of the worst thing that can happen in the system and the magnitude of the worst thing that can happen in the system, we can see that these are very small. So meaning that they are more unlikely and they will take less load in the worst case. So what we saw with this very simple example was that, you know, in fact, optimizing or investments for reliability are not the same as investments for resiliency. And sometimes, in some cases, when we are investing in resiliency, we might not invest in reliability, and there is a trade-off with costs. And what we did afterwards was to extend this exercise a little bit further, and we add two new situations. So now we look at this feeder, and instead of hardening the south part, we decided to harden the north part, basically mirroring what ComEd has now in their reliability plan. And we also considered another plan that was a little bit or was way more expensive, which was basically considering a full integrated, full connected hardening of this part and operating all of this feeder at 12 kV. So this was, of course, a way more expensive solution, but we still can derive their reliability and resiliency results. And of course, as we can see, the changing basically the north or the south, which is like these red and blue bars, SAD and SAFE, they are one is better in duration, the other is better in frequency, but they are equivalent. And of course, actually the combined system and like the full integrated hardened system is actually the one that brings like better safety and safety. And the same with resiliency. So when we actually look at the impact of this the full hardening solution, we can actually see that, you know, it not only improved decreased the risk of not serving demand significantly, but it also improved what could happen in the worst case in the system. So what we can see here is not only that there is a trade-off between reliability and resiliency, but also the only way we can address both sometimes, and we are, you know, we can actually make sure we address both is by spending a lot of money in the investment. So it's very important. That's why we need like tools and analytical ability to being able to describe trade-offs between this reliability, resiliency, and cost. When we go back to our objective, the objective of this project and what our tool does is mostly to optimize this and make this an explicit objective of the planner or in the investment and planning process. So what we have actually is a cost versus risk model, where we optimize the investment operation, joint optimization of investment and operation, like the typical capacity expansion problem. But we consider this stochastic. We consider the uncertainty of outages and the uncertainty of load, of not serving the load, and we model the expected cost of not serving the load and the CVAR of the cost of not serving the load. And this expected value is going to capture more the routine aspects of these outages, whereas the CVAR and the risk are going to capture more the tail of the outage events and the tail of this distribution of outage events. So, and we add this lambda, and lambda is a parameter that is, is used by the planner to choose the level of risk aversion. So, how much we care for reliability when in comparison to risk. We join minimize this function, and we consider a loss of load cost. So, how much, what would be the cost from either from a utility perspective or from the consumer perspective, depending on how are we actually using this exercise for. If it is like for a pure investment cost minimization from utility perspective, or from just a welfare minimization perspective, but we always consider like this joint minimization of cost. And we consider, of course, the technical aspects. So nodal balance constraints, load flow constraints, substation limits, DER limits, and sometimes coupling constraints, especially when you consider batteries and ramping of generators. So when you look into the results, we have, like, for example, this preliminary case study we just did. So we are now the phase of demonstrating this with ComEd. So now this as actually an optimization and decision support model, and we tested this first in a preliminary case study involving just a feeder, a relatively small feeder with 54 nodes, 7 megawatts feeder, and we consider 1,263 scenarios of routine failures, 100 scenarios of high impact low probability events, and this feeder comes with like 22 candidate lines, which is these dashed lines here, and we also considered 4 potential nodes to install batteries, which are the orange ones, and we considered 4 types of potential candidate nodes to install distributed generation, which are the green ones. So, and then what we did is let our model to decide for different risk aversion aspects, decide what would be the best solution. So when we would not consider any risk aversion, so setting lambda equal to 0, we are only caring about the expected value of the expected cost of the loss of load. So this is the solution we obtain. There's like some new investments here happening in the lines to kind of improve the connectivity in the circuit. There is an installation of a 8 kilowatt hour natural gas distributed generation, and was one small investment in a battery. When we increase the risk aversion, so when we start also caring not only for reliability, but also for some resiliency and for the tail aspects of this curve, we start seeing actually more, not only more line connections. We see the same distributed generation here as an optimal solution. We see some new lines here, but above all, what we see is like our model not only increased the number of batteries, but also diversified the position of this battery. So trying to actually use all the potential of placing of battery to kind of edging against the risk. And when we analyze, the results in terms of reliability and resiliency, again, in reliability, we look at energy not supply, the distribution of energy not supply, as you can see in the first graph, and you look at the steady and safe feed. What we see is then, when we have the first case with no investments, the lambda equal to 0 and the lambda equal to 0.5. So when we both care for resilience and reliability, what you can see is then when we change lambda from 0 and 0.5, actually we don't change much the SAD and the safe feed. So already the lambda equal to 0 makes a significant impact in the duration and frequency of the system, which means that when we actually just look at the expected value and minimize the expected value of the expected cost of the interruptions, we see already an improvement in the reliability. But when we look at the resilience analysis, what we see is like we have to actually bring lambda to 0.5 to improve what can happen in the worst case scenarios, to actually shift this curve to the left and have all the events or most of the events in this area, which is like very little impact in the network. And that basically is what happens with this lambda equal to 0.5. So we actually need to tweak those batteries, to install those batteries, to improve the connectivity of the network, to actually be resilient, be more resilient, and to capture the risk and mitigate the risk of this. And when we look at this bottom right chart, and we look at the different investment costs, this is costs for lambda equal to 0 and lambda equal to 0.5. So if we only care about reliability, we care both for reliability and resiliency. And what you can see is that there is a different costs, and this difference of cost here, we could call it the risk aversion cost. It's some sort of insurance policy that we pay just to make sure we address those high impact probability cases. And most of this cost, as you can see, is a battery or lines cost. So we believe that this type of analysis is very important and this is what we are demonstrating now with Commonwealth Edison, is that this type of analysis is very important to help utilities justify their costs and actually they transpose their costs into actual reliability and resiliency targets. And how to actually use this as an instrument for conversations between utilities and regulators. So we are very interested in pursuing this objective. So just to wrap up this final slide, just a little bit of what the next steps are. So we are now in the process of demonstrating this phase, this distributed generation and optimization part of the method with Commonwealth Edison. So we have a prototype tool. We want to also expand the type of investments we are considering. So considering more distributed automation, microgrid formation, capturing uncertainty of renewable energy generation. So not only the uncertainty of the outages, but also, especially when you consider distributed resources, we want to capture the uncertainty of the availability of the primary resource. So in this case, uncertainty of solar, and also accommodate part of the transmission grid expansion planning in this process. So how, what are the effects? How can we? What are the impacts of the distribution investments in the actual transmission grid plan. Other potential applications, we want to use this to kind of quantify and to help uses more as evaluation tool to kind of quantify how much each technology can change the resiliency of the system in different technology, in different cases and different scenarios. Using this, as I said, as a cost versus risk transparency model for conversations between utilities and regulators, and how also to apply the same principles now that we do for investment planning. How can we bring this to the operation and especially to the operational planning when you're making decisions hours ahead of the event? So how can we model expected value of costs and CVAR of costs when we're talking about shorter term uncertainty? For example, how to make decisions or risk-based decisions explicitly for PSPS events. So now with that, I will stop and be open for questions.